I'd like to welcome everyone to the NGL webinar. We're fortunate today to have Brett Maurer from University of Washington making a presentation. Brett got his bachelor's degree from Syracuse University, master's and PhD from Virginia Tech. In 2016 and 2017, he joined the University of Washington faculty and has been a colleague of mine and the rest of our group, and is off to a tremendous start to his career. He's gotten a career award from NSF, an early career researchers award from USugar, a Casa Grande award, and a Norman Medal from ASCE, and he's gotten teaching awards from the University of Washington. And having sat in on his lectures, I can tell you that those are very well-deserved awards. And so Brett has been working in the area of liquefaction, working a lot with the New Zealand data, but other data, and has done some really interesting work. And today he's going to be talking about artificial intelligence and machine learning and their applications, or perhaps lack of applications, in the field of liquefaction. So Brett, with that, I'll take it away. People, if you want to ask questions, you can put them in the chat, and we'll have a discussion after Brett's finished his presentation. So it's all yours, Brett.
Yeah, thank you, Steve, and thanks to everyone for listening in. I want to just quickly acknowledge Morgan, who's a grad student that co-authored what I'll be presenting, as well as Mekchan Gayan. Mekchan is at NGI, but he formerly worked with me, and together we learned a lot that underlies what I'll be talking about. Obviously, AI really dominates the news, but I would say this for me started about 10 years ago, because I noticed as a student that there were a lot of AI liquefaction papers, and I noticed that no one used them. And so I would talk to my advisor, Russell Green, at the time about, why he thought that was, and he shared some ideas that I think eventually evolved into this. So before I start, I just want to plug two potentially relevant items. One is a set of new CPT case histories from the Nisqually earthquake, which is now over 20 years old, but I think these are the first CPT case histories. And so these are on DesignSafe. Second is an editorial that will be coming to GeoStrata, but you can look at it online. This is on the use of ChatGPT in geotechnical engineering. I'm sure many of you have kind of tested what it can do. As we did, we gave it geotechnical exams and test sets, really interesting outcomes, I think. Most recently, we asked ChatGPT to read a paper that we had written, Morgan and I did, and to write an abstract with a specific number of words. It wrote a beautiful abstract, and then we submitted that abstract to GeoCongress, which I think provokes some questions and thoughts for sure. So an outline that I'll keep coming back to as I move through. The backdrop kind of has a few converging parts. First, I want to highlight this really interesting paper in GeoStrata by Brett Lingwall and Kevin Franke on increasing the impact of research on geotechnical practice. And as one part of the strategy, Brett and Kevin write, the average practitioner doesn't have time to read the literature. Even if they do, it's difficult to understand the different approaches. There's just too much information. And so filtering efforts are essential. And this really struck a chord with me. And I think in the context of AI liquefaction papers, it's definitely true. And I think it's even more true for researchers and less true for practitioners. I'll get to why that is. Also inspirational was this review paper in Earthquake Spectra by Shi et al. This was the most cited earthquake spectra paper from 2020. Way more citations than the National Seismic Hazard Map update around that time. And so they looked at 200 AI papers, including 25 on liquefaction. These are all in earthquake engineering. And they conclude that AI liquefaction models outperform state of practice or SOP models. I'll use the acronym SOP a lot here. And they include Bollinger and Idris. Okay, so the models are beating that. And when I read that, I had three thoughts. The first was, well, I see why people who read these papers think that's true. Second, I don't really think that's true. And third, if it is true, why don't people use these models? I think we can say with confidence that most liquefaction models published to date have utilized some kind of AI. So I'll just repeat that. If you do something in liquefaction and you're not using AI, statistically you're kind of uncommon. And yet no one is using these AI models. So this is an extreme example, but Yout et al. Model everyone, paper everyone is familiar with, over 3,000 citations. 75 other models that use AI that I'm going to talk about here, they have a total of 2,400 citations. And it's not just a matter of, model maturity. So we're looking here at the number of citations per year. I've pulled out 10 models that I would call SOP models. These are all triggering models based on the same framework. And these average 76 citations per year each. Obviously, some of them are a lot more than that. The 75 AI models, which are these gray dots that I'll talk about, they average only 3 to 4 citations per year. And I'll also just point out that some of the AI citation counts, you see some markers up around 20, they're kind of questionable. And I'll just leave it at that. On top of that, we couldn't find a single use of AI liquefaction modeling in practice. We couldn't find a building code, design manual, textbook that even mentions AI liquefaction models. And so you might think if most liquefaction models use AI, then surely the new textbooks are going to talk about these models. I haven't asked Steve and John about this, but I'm just going to guess that there's not a chapter in their new textbook on AI liquefaction modeling. So it's really the case, in my opinion, that no one is using these models besides the people that develop them. So our aim here is basically to try to get to the bottom of this. Why is this happening? And I'll say up front, there's some good reasons. I think there's just so many papers, unfortunately, that it's really difficult to pick out those that are potentially more innovative. And I'm just suggesting that we try to, separate the wheat from the chaff. There's a lot of chaff to be sure. And I think the outcome, unfortunately, is that a lot of people have very negative associations with the word AI. If they see AI, they assume a priori that this is something I can just ignore. I don't need to worry about this. And I really think that's a mistake, even though I totally understand, because empirical models and model components are really ubiquitous in liquefaction modeling. And if they're useful, clearly they're useful because we use them, then why not AI? There's not a good defense against that. And so I think to say that you should stay away from AI, but then use something empirical, I don't think these are coherent ideas. So specifically, we're going to look at 75 papers. So we read 75 papers that developed AI liquefaction models. And we wanted to try to figure out what are the problems so that they can be understood and identified and hopefully corrected. And then, is there some wheat here in the chaff? Maybe there's some papers that don't make these problems that maybe kind of point to applications where AI could be more useful in the short term. Okay, so what is this literature that we looked at? 75 papers, 65 were in journals. Most of the conference papers were in ASCE proceedings published over the last 30 years. This was representative, it's not exhaustive. You'll definitely find more papers. We set up alerts, Google Scholar, etc. And it's like every week there are more and more papers. Soil dynamics and earthquake engineering had the most with 14, but there were a lot of, let's say, top journals with papers: Computers and Geotechnics, the ASCE Geotech Journal, Earthquake Spectra, Engineering Geology, Canadian Geotech Journal, Soils and Foundations, Bulletin of Earthquake Engineering. The point is this: these papers are coming from journals that you publish in, that you're familiar with. We're not pulling these from real mysterious corners of the universe, although maybe a couple do come from mysterious places. So, not surprisingly, the number of papers is increasing annually. We went from 5 in the 90s, 26 in the 2010s, and the 2020s are on pace for 80. I think it's going to be a lot more because that's just a linear extrapolation from the last 2 years. I think we're at something of an inflection point, and it could be hundreds of papers this decade. So I think it's timely to try to address this body of work, to try to make sense of it, and maybe we can shape its direction and its perception for the better. So these 75 papers all make some kind of AI liquefaction model, and I think it will be useful to try to place them in context with SOP models. So let me just quickly kind of define the hierarchy as I see it of SOP models. So first we have geospatial models. These basically make inferences of what's below the ground using data from above the ground. And of the papers we looked at, 5% of them would fall in this category. Next, we have our stress-based models that use in situ test data. I would say this includes both triggering models and manifestation models that predict lateral spreading, ejecta, general ground manifestations. And of the papers we looked at, 75% of them were basically tier 2 triggering models, and 20% were tier 2 manifestation models. Tier 3 would be numerical constitutive models, and we didn't look at any of these. There actually are now some AI constitutive models, but we thought we were sort of taking on enough as it was, and that we would confine our scope to tier 1 and tier 2, as we call it. I should probably say something about AI tools without saying too much. AI doesn't really refer to anything specifically at all. It, for me, just refers to an algorithmic or automated approach. Most of the papers we looked at were using neural networks, which some people call deep learning. Some people say only neural networks are AI. They make that distinction. Also popular, though, were decision trees, which are built and ensembled with bagging and boosting and random forests. We saw support vector machines, Gaussian process models, and some other techniques, most of which can be applied both to class problems, so classification like liquefaction triggering, and to continuous or score or regression problems. That would be like predicting lateral spreading displacement or ground settlement. I don't want to try to summarize the mathematical details behind these things. First, I don't think it would be interesting. And second, I might injure myself trying to do that. What I do want to do, though, is try to generally lay out how AI approaches differ from traditional statistical models. The first is that AI is really based in the pragmatic. It cares about predictions. So predictive performance speaks for itself. It's not so important why the model works. Okay, that's one clear feature. And so some models are so convoluted that it's almost impossible to explain them. Others now are interpretable. or explainable. And that basically means that you can rank the importance of predictor variables. But exactly how the model works is almost always unknown. But I would say in business, the governing fundamentals are often quite abstract. I mean, there's no expectation that mechanics should be explaining what you're trying to predict. You wouldn't expect that there should be theoretical models to select online ads. You wouldn't say, I think Alexa and Siri would be better if they respected mechanics more, because these models learn from examples. And I would say there's a lot of analogs in geotech. If you said, will a theoretical model relating ground slope and subsurface shear wave velocity be discovered? Well, no. And what does that even mean? It's like an abstract question. But it's clear that ground slope is useful for predicting VS. Number two, AI models tend not to be portable and executable by hard copy. There's a few exceptions, but in general, if you don't give people code or software, no one can run the model. The exceptions would be if you can somehow store the predictions in advance. So this is an example of a map of VS30 that's been predicted by a machine learning model. And so the predictions are stored in a map. You don't really need the model unless you want to go run the model somewhere that it hasn't been run. But in general, you've got to have code or software. Number three, AI modelers tend to work with many more variables, more types of variables, and they just do it so much more easily, because AI is a lot less dependent on having hypotheses of what is believed to matter and how it's going to matter. And so we see models with hundreds of variables. You can imagine if you're looking at demographic information on internet behavior, you can compile a lot of predictor variables. And then lastly, if you're going to use a lot of variables, that creates two additional needs. First of all, you need a lot of data. If you're going to elucidate the predictive power of all this information, you need a lot of training targets. And secondly, overfitting is a big problem in AI modeling. This is where your model does great on the test set, but really poorly on unbiased data. And so techniques to control overfitting, unbiased testing, k-fold cross-validation, ensembling models, they should really be routine in AI workflows. So as a quick summary example, let's look at the Youd et al. Classic model for lateral spreading that many people are familiar with. I would say in a lot of ways, this is not very different from AI, truthfully, but probably an AI modeler attacking this problem, they would look at a lot more variables and it would be easier to do that. They would split the data into lots of parts. They would train and test on all the different parts again and again. They would develop not one model, but many models, and they would ensemble those together. They'd probably be able to tell you what variables are important, but I doubt they would be able to explain exactly how the model works. And so they would have to give you code. They wouldn't be able to give you an equation on paper. But I like to imagine that, the AI modeler would meet you in a dark alleyway, and they would say, but do you really understand Youd et al. Either? And in any case, don't you just want to make good predictions? And I wonder, would they be wrong asking those questions? Okay, so we looked at these papers and came up with 5 recurring shortcomings. Okay, the first one, AI is definitely perceived to be more complex and less transparent than SOP models. I would say truthfully, AI models are easy to run, but they're definitely opaque and complex in their underpinnings. And so if you expect someone to use an AI model over one that is more transparent and trusted and familiar and widely used, you've got to prove the AI model. That just seems obvious. And so it's really surprising that of these models, 2/3 of them made no comparison to any existing SOP model. Of the 1/3 that did, some of them tested against outdated models from the 70s and 80s. Nothing against those models, but they're not testing against the latest models. And some of them clearly implemented the SOP models incorrectly, say mixing and matching different parts of models that, you just can't do that. Some papers alluded to performance comparisons without actually providing any. One paper said the behavior of the neural network was consistent with prior knowledge. Another said this rate of prediction is about the same or a little higher than those achieved by traditional methods in practice. Right. Other papers kind of established odd measures of success as a way not to do any real test. One paper said, based on accepted standards, it was decided that predictions within 50% of the measured horizontal displacements were successful. So I don't know that standard myself. And then another group, they claimed success when their AI model beat another AI model they developed by 1%. Now, I think we should point out that our SOP models aren't so good at this either. I don't know of any tier 2 triggering model, for example, that compared against any other triggering model when it was developed. And I think that's true of most manifestation models as well. So, we shouldn't throw stones when we're inside the liquefaction research compound. Nonetheless, I think the question persists. Why should someone use a model that hasn't been shown to outperform a simpler, more familiar model? I'm not sure that they should. Okay, number 2 is some bad practices. So in addition to not comparing against SOP models, we noticed 3 recurring things. The first one is relying on overall accuracy as a performance metric. So about half of the papers used only overall accuracy to optimize or measure performance. And so overall accuracy is the ratio of accurate predictions to total predictions. So very simple. The problem with OA is that it's really sensitive to sampling imbalance. And liquefaction data is almost always class imbalanced. And so if you consider a hypothetical data set with 99 positive cases and 1 negative case, imagine that you have a model that no matter what input you give it, it just says liquefaction. It's not really a model. It would have an overall accuracy of 99%. So the model is basically useless, but overall accuracy says it's great. And so the point here is that if you optimize a model on imbalanced data using OA, it's going to have the illusion of superiority. And then if you turn around and test it on imbalanced data, it's going to look much better than any model that you're comparing to that's not biased. Now, you can't just assume that anyone that uses OA is doing something wrong because you can resample your data, but a lot of these papers did not. Number 2, overfitting. Okay, so AI is like a high-order polynomial. It can separate 2 classes of data very efficiently because it's permitted to be very complex. That does not mean that it's going to do well on unbiased data. And so overfitting prevention is something that you have to do with AI workflows. Okay, so we look at these papers and quite a few of them report efficiencies of 99 or 100%. Okay, and that's kind of eye-opening because that means the problem of liquefaction is solved. Okay, like, didn't you get the news? Everyone can go home. Liquefaction has been defeated. But people who have studied liquefaction know that it's really complicated. And there's been some large analyses of global case history data that basically suggest our tier 2 SOP models are something like 70 to 85% efficient. There's a lot of ways to measure efficiency, and it's going to vary event to event, but that seems to be about how our models are doing. And so it's really suspicious that an AI model could be 100% efficient on the same data. When you look at these papers closer, they are most assuredly overfit. They are not doing anything to prevent overfitting. And so I'd say you should be really skeptical of papers that report efficiencies much higher than say 70 to 85%. Okay, the next kind of bad practice, the last one, was problems stemming from small data sets. We're looking here at the number of data points or case histories that the different publications used. Most of them used less than 250 data points. Some even used less than 75. First of all, we have to ask, is the test set meaningful with this little data? So typically, when you do unbiased testing, you reserve 10 to 20% of your data. And if you're starting with very little data, that may be just 10 or 40 data points. And those data points may be really easy to predict. They may be really similar to points in your training set. And so that alone may explain some of these really high efficiencies that are reported. We also have to ask, are these performance differences statistically significant? Performance metrics are much more uncertain when they're based on small amounts of data. One model may appear to be better than another, but is the difference statistically significant? It's a really important question. Of the 75 papers, just one tested for significance. Meanwhile, studies have looked at our SOP models, and they have seen that differences between SOP models are rarely statistically significant, even when you're looking at hundreds of case histories. So the models are just too similar, the amount of data is too small, the uncertainty of the performance is too great to say that the differences are significant. And so, unless it's proven otherwise, I would assume that the differences between AI and SOP models are not significant. Okay, I want to go back to those numbers for a second. Some of the models used thousands of data points, which is great, but it begs the question, how did they do that? When we look at our triggering case history data sets, now NGL is growing these numbers significantly, but the well-known data sets have hundreds of case histories. Lateral spreading, for example, I think is similar. And so, well, how did these models use so many data points if there aren't that many case histories? Well, some of them used the new Canterbury data, but some of them did not. And that leads to the next shortcoming. Okay, is the use of AI useful? It's really important to ask, what exactly are you doing with AI and why might it be helpful? Unfortunately, a lot of papers don't address this. I think they're predicated on the fact that AI is impressive and mysterious, and that alone is the foundation of the paper. We saw 3 applications that I want to discuss quickly, and they all involve tier 2 triggering models. First of all, 7% of the models were not actually trained on case histories. They were trained to predict the predictions of SOP models using the same inputs as the SOP models. So that explains how some papers used a lot of data, because a single CPT has thousands of data points. And if you predict liquefaction at each data point, that becomes a target for the AI. It's interesting, but I don't really understand the purpose. You still need all the same inputs as the SOP model, and you're never going to do better than the model you're trying to mimic. It's also another explanation of those high efficiencies. They're not actually testing the model to predict liquefaction. They're just testing its ability to mimic another model. Second, we saw 13% of papers propose new limit state triggering curves in the space of CSR versus CRR. So I want to ask the question, if you reduce liquefaction to this bivariate space, do you really need artificial intelligence to draw a line that separates these data points? One paper kind of answered that question. They said, the limit state function obtained by neural network does not seem to be better than the one obtained simply by drawing a boundary curve. And I think to reduce liquefaction to a bivariate curve is kind of the domain of traditional regression. It's not really the wheelhouse of AI. I get why you would do this, because you can then present an equation where AI is kind of behind the equation, but you're not really using AI to its full advantages. Okay, lastly, we saw a lot of papers develop AI models using the raw ingredients of tier 2 SOP models. So I'm saying tip resistance and sleeve friction and depth and fines content and etc. On the one hand, this seems totally reasonable. This is what AI is about. Give it a lot of predictor variables that you think may be important and see what it can do. At the same time, I think it's really questionable to reduce the stress-based framework to these raw ingredients when you have such little data. Let me give you an example, but there's others. The stress reduction coefficient, R sub D, integral to all triggering models, to my knowledge. R sub D is trained independent of liquefaction data using site response analyses of many, many profiles and motions. So the Green et al. R sub D model, for example, is trained on 400,000 site response analyses, millions of data points. When we look at R sub D, we are looking at human intelligence of wave propagation mechanics, and we're looking at insights from many thousands of profiles and motions, okay? So when you remove R sub D, you are removing human knowledge, and you're asking AI to basically rediscover that knowledge from liquefaction case histories. Now, it's not impossible in itself, but do you really think AI is going to learn more about R sub D from a few hundred data points than humans have learned from millions of data points? And on top of that, I think people are asking AI too much. They're asking it to understand the influence, not just of, say, depth, but of every factor, and to do that with just a few hundred data points. I would ask, isn't it better to isolate important factors and to study those factors with additional data, knowledge of mechanics, even if that is unfashionable? So it's impressive that AI can do what it does, without human insights. It produces models that seem to be reasonable. But I would ask, is AI being used optimally or innovatively or to any advantage? And I could keep going. We saw a lot of notable things. One final, very brief example. The latest trend is explainable or interpretable AI, which is a very important movement. The idea is, let's at least be able to rank the importance of variables. One very recent paper did this. They made an explainable AI model looking at 13 predictor variables, and they concluded that the two most important variables were tip resistance and PGA. Okay, so I'll just leave it at that. I think you know what I'm getting at here. Another really similar paper, they looked at SPT case history data, and they discovered that liquefaction depends on below count and fines content. So I think we should be suspicious when AI papers don't say exactly why AI should be advantageous. Does AI facilitate some new modeling approach? Does the model outperform existing models? Does the model say something new about liquefaction? I really think one of these answers at least should be yes. Okay, the last two are interesting. So the woo-woo effect. What I'm referring to here is the very complicated language of AI modeling papers. I like to refer to this also as quantum spookiness, to borrow a term from Einstein. It's very common to read sentences like this one. An imperialistic, competitive, meta-heuristic algorithm incorporated with a multi-objective generalized feed-forward neural network did such and such. This is very common, right? And there's not necessarily anything wrong with this. The point is, does the user understand what they're reading? There are so many different workflows in AI. Every technique has many, many hyperparameters. These are the options of the model itself, not the predictor variables. There's different ways to sample data, different ways to optimize, to stack. Stacking means ensembling. It means let's do machine learning with other machine learning models as inputs. So there's an endless array of workflows. And you can potentially give every workflow a new name, make it seem like something new. And indeed, we see this. So through the 75 papers, we encountered models that were said to be inspired by all kinds of things. Honeybee swarms, ant colonies, the hunting behaviors of gray wolf packs, the predatory instincts of antlion larvae, which are these creatures, whales. Still other papers were inspired by adaptive resonance theory. They used neurofuzzy systems and canonical correlation forests. They blended hybrid wavelet networks with particle swarm optimization. Those are those honeybees. And they had features like T-distributed stochastic neighbor embedment, which everyone knows is very important. And I do wonder if this jargon gives the impression that something new is taking place, even though fundamentally many of the papers are doing almost the very same thing. And so I don't want to make light of these algorithms. They clearly have innovative roots and uses in computer science, but I think a simple truth lingers. If geotechnical engineers don't understand the utility, no one is going to use these models. And I think when you kind of lift the veil of impressive terminology and AI, you see that many models are doing something very similar, something that I would say is questionable. They're using the same small case history data sets, and they're training models that I just don't think are any different or any better specifically than SOP models. So finally, we have failure to launch. Now, I mentioned that with few exceptions, you have to give people code or software or no one can use your model. And it's therefore really surprising that AI models are rarely provided. So across these papers we reviewed, 84% provided no way to use the AI model. 3% said they'd provide it on reasonable request. And yet we made requests that I thought were pretty reasonable, and we didn't get any more models. So it is the norm, rather than the exception, to describe an AI model without actually giving it to anyone. Now, I don't think that's unreasonable in all cases. When you're doing exploratory research, I think it's fine to talk about the potential of something, even if you don't have a finished product to give to people. But should it really be 87% of the time? we've kind of been at this for 30 years, and it seems like at some point we should be making models that people can use. I think it's hard to imagine this passing as acceptable in other contexts. What if Darcy discovered a law that governs flow through porous media and wrote a paper about that discovery, how well the law works, but never actually provided the equation? What if Yao et al. Developed their lateral spreading model, talked about how they did it, talked about the performance of the model, but didn't put the equation in the paper? You would think that something was wrong, I bet. So, why is this happening? And I don't really have a good answer, but I wonder, maybe editors and reviewers are just not yet familiar with AI tools. That, it's all very new. Maybe people are just disoriented by quantum spookiness. I totally understand that. Maybe people just have a different philosophical mindset than we do. A different idea about what you should do when you publish a model. Now, what about the authors? They know what they're doing. They know that they're describing models that cannot be used. So why are they doing this? How did this become normal? What is going on? I have a lot of questions. I don't want to get conspiratorial, but I just don't understand. I don't know how else to put it. This really confuses me. What I do know, though, is if you don't give people a model, no one will use the model. And if there had to be one answer to the question of why don't people use AI models, it's because in some sense there is no model to use. Okay, so having kind of finished my rant about all the reasons I think the models have been ignored, how about very briefly just some applications, some models that maybe you shouldn't just dismiss. Maybe you shouldn't be cynical wholesale about AI, even though there's some reasons to be. I don't know if it's a coincidence, but we noticed that tier 1 geospatial models and tier 2 manifestation models were much more likely to be free of all of those shortcomings that I talked about. That was only 25% of the papers we looked at, though. More broadly, it seems like AI is best applied in one of two cases. First, where predictors and a target are correlated but not mechanistically linked. So there's no expectation that mechanics should be controlling the relationship, like when you do geospatial liquefaction modeling. Or second, maybe the predictors in response presumably are linked by mechanics, but those mechanics are really poorly understood. So maybe in the case of predicting manifestations from triggering. Okay, so a couple quick examples. And I don't want to give the impression that I'm, endorsing any model as something that you should, stop what you're doing and go use. I'm just saying I don't think you should a priori ignore models. A couple geospatial examples. This one from Todorovic and Silva, a liquefaction model for regional analysis. This is similar to the geospatial model of Zhu et al. It's a decision tree ensemble, only 6 predictors, used cross-validation, gave some evidence in unbiased testing that they did better than existing models, and they put their model in software in the OpenQuake engine out of Europe. And so it seems like this was going to be used in Europe. Another example from Guyan et al., an AI-driven, mechanistically grounded geospatial model. This one's a little bit different. It doesn't predict liquefaction directly. It instead predicts in situ test data and then uses the latest tier 2 models. In effect, that's what it does. And so basically it parses the problem into that which is empirical and data rich and probably best predicted by AI, This is the part where you predict below ground conditions with above ground data. And I say it's data rich because you don't need case histories. You just need in situ tests. And we have conceivably millions of in situ tests. It leaves the part that is data poor and probably best predicted by mechanics to the mechanical models. Okay, so this is the predicting liquefaction conditioned on subsurface traits. And so maybe this is an example of how AI and mechanics can get along harmoniously. AI looks to understand the empirical patterns constrained by a mechanical framework. Lastly, it did the things that you should do: unbiased testing, cross-validation, model stacking, combining lots of different types of AI models, significance testing, and the code is put into some Windows software that's shown here on the right. So it's easy to use. Okay, manifestation models, I would say, compared to triggering models, have been based much more on intuition. And I think the reason is clear. It's because liquefaction manifestation is a very complicated hydromechanical phenomena. Now, the gap between triggering and manifestation is definitely shrinking, but it persists, and I think it's long invited empiricism. Think about that Youd et al. Model that everyone knows that I showed you. So this is a prime target for AI. Let me just give you some examples. So Oman and Bayes developed a lateral spreading model using support vector machines. They did cross-validation, test versus existing models, and they provided the code so that you can use the model. Durante and Rathje also developed a lateral spreading model using a decision tree. They used a lot of data from New Zealand. They blended kind of a unique, it's a unique approach where they use both subsurface data and sort of above ground geospatial data. They did cross-validation, unbiased testing, they gave you the code. Lastly, Rateria and Maurer, they make a model to predict liquefaction ejecta, and it does the things that you might kind of hope. It checks the boxes. So I think the models that I've highlighted, they seem like reasonable uses of AI. Of course, you know, everyone has to decide that for themselves, and they adhere to best practices. Most importantly, you can actually use these models and you can tell everyone else whether they work or not. And unfortunately, you can say that for very few papers in the literature. Okay, so in closing, no one is using AI models, just about, other than their developers. We looked at the literature and we came up with some good reasons for why we think that's happening. So these models are not compared to SOP models, making it unclear why you should adopt them. They depart from various best practices, making it unclear how they actually perform. They use AI in some ways that, you know, I think are questionable, and they're really confusing. And that makes it hard to understand what the benefit or novelty or innovation is. And they're presented but not actually provided, making it unclear how, you know, anyone could actually use the model. And so, you know, all of this together just seems like a real big mess, to put it nicely. The good news is it seems like there's a game plan for stopping it, you know, and I maybe stopping it's not the right word, but I would say shaping the direction and perception for the better. And, you know, I think together we can do that. I don't want to give the impression that all of the work thus far has been without merit or utility. It is definitely the case, in my opinion, that AI will play a role in the field. I think that train has left the station. And so to that end, I briefly have pointed out some applications, some papers that maybe provide examples of how things could be done in a better way, and maybe where value will be found in the near term. I think AI might improve tier 2 triggering models, but I think it's going to come likely only in conjunction with other important improvements. Fundamentally different modeling approaches, different types of in situ test data, new in situ tests, way more data. I wonder, if it was going to improve things, maybe it would have already. And I would say, whatever you do, I would like to think of that checklist as, almost something that journals might adopt, when we look and think about AI models. So with that, I will kind of finish my rant again. I hope it was somewhat entertaining or useful, and I'd be happy to talk about any parts of it. If you want to talk about quantum spookiness, I'd be happy to do that.
Okay, well, thanks, Brett. We very, very enjoyable. I'm getting an echo here on my end. You've really done a nice job of kind of laying out where things are. I know for myself, I see some of these papers, I glance through them. I don't know the various algorithms and approaches well enough to make an informed judgment about them, and I would struggle reviewing a paper that is heavy on the AI and ML stuff. So that certainly is one of the important challenges. You pointed out a number of things that I had thought of as prior to your presentation about limitations of these types of approaches. I wonder, since I've got the floor, I'm going to take advantage and ask a couple questions or for a couple comments initially. One of the big problems we've always had is extrapolating beyond the data in our case histories. For example, we're limited to relatively shallow depths because we've put an emphasis on manifestation in interpreting case histories. But if you're working on dams and large structures, you may be interested in the potential for triggering of liquefaction at very large depths, hundreds of feet even. And then the second part would be on quantification of uncertainties and how you think AI approaches are suited towards that sort of thing as we move towards kind of probabilistic liquefaction hazard analyses and performance-based analyses. What do you see there?
Yeah, thanks, Steve, for those questions. So on the first one, I would emphasize, of course, that AI is an empirical model, and no matter how sophisticated it is, it doesn't know what will happen beyond the boundaries of the data. Everyone has fit a curve to data that does wildly inappropriate things when it leaves the domain of the training data. It curls upon itself or it goes negative. And so that is definitely an example of how you really need mechanics and human knowledge to extrapolate and constrain a model in a reasonable way. On the question of uncertainty, I would say broadly that is something of a shortcoming of AI. When you think about, business applications, for example, companies want to make a prediction. They want to know how the consumer will react. There's not necessarily a need or much interest in quantifying the uncertainty of the prediction. There are AI techniques, though, that are better at that. So Gaussian process models, for example, are inherently a probabilistic technique. So they're giving a distribution of the prediction. But again, so I will also just point out that you can, of course, make a model and then retrospectively derive information about the uncertainty. A lot of people, that's how they quantify uncertainty. But in terms of inherent to the methods themselves, do they quantify uncertainty inherently? I think that's a weakness.
Okay, well, thank you. I see Scott Brandenburg's got his hand up.
Yeah, thanks, Brett, for a great presentation. And thanks also for putting yourself closer to the dumpster fire than me. I don't know if it was me.
I wasn't going to use that term, Scott. But...
You didn't use the term, but I saw the picture, and I can recognize images with my own brain. Hey, my question is related to kind of the potential for misclassifying data, because however we're going to train a model on data requires incorrect classifications. So you distinguish between triggering models and manifestation models. And I would argue that when manifestation happens, we do know that manifestation happened. There's ground cracks, there's sand boils, things like that. Triggering is much more difficult for us to know, because I think that there can be triggering without manifestation. And so for a triggering model to work, which would be based on things like penetration resistance and the cyclic shear stress demand on that soil, or maybe other things, fines content and so forth, you really kind of do need to know what happened to that layer. And I think that it's possible that we have had triggering of layers that just didn't manifest because of system effects, the crust is too thick, something like that. And then also, I think classical triggering models are by extension, therefore, kind of a blend of triggering and manifestation, because the classifier is based on manifestation, but the identification of the critical layer, right? How do you pick tip resistance for manifestation? It has to be a layer property. So then we have to identify the one critical layer whose properties are representative of the whole profile, which may introduce problems in the classifiers too. So I'm just wondering, on the data side, do we have problems that are inhibiting accuracy of these AI models?
Yeah, thanks, Scott. I think that's all really well articulated. Liquefaction is a hard problem because it's an inverse problem. We can have the very same surface effect that has arisen from infinitely many combinations of subsurface response. And I'm a big believer in the idea of developing triggering and manifestation models iteratively and harmoniously within a consistent framework. I don't know if that, in the future will be how it's done, but I also, I don't have a great, answer. I think there's definitely this problem, this upfront problem of the uncertainty of the data itself. Is it even a manifestation case? Because we'll push a CPT next to a sand boil or 100 meters from a sand boil, and that's uncertainty. And then we have the uncertainty that you alluded to. So I do think that AI will eventually improve triggering models, but as I said, I feel like there's got to be more to it. There's got to be a smarter philosophy, something new. I don't think that if you just give AI the traditional inputs and see what it can do, that it's gonna produce something that we should all use.
Yeah, thanks. I agree.
Okay, well, we're about at the end of our scheduled amount of time. I don't know if we have a restriction from the setup of this team's meeting, but I think we could probably go ahead, and if people need to drop off for other activities, they can go ahead and do that now. Brett, if you're willing to take a couple more questions, we can continue a little bit, those of us who have time and are interested.
Sure, if there are some.
Yeah, I'm trying to look through the chat now. I see Ben Mason has a question. I don't know, Ben, if you're on, or do you want to unmute yourself and ask it, or we can just read it off from the chat.
Yeah, I think this works pretty well. Hey, Brett, thanks so much for spending some time with us. That was awesome. And I think you've used a very specific example with AI, though I've thought about other fields that I'm interested in, and very similar types of thoughts. Regardless, my question follows a little bit from Scott's, and he asked part of it, so I won't repeat that, but I'm almost wondering if we should start thinking about, especially these standard of practice models, so tier 2. The examples you used in the conclusions were all kind of manifestations, right? Lateral spreading and how it could be used for that. But I'm talking about actual triggering models.
Mm-hmm.
Do you think that just because this is such a field focused on empirical data, engineering judgment, human intelligence, that at least in our academic lifetimes, that AI is not going to really play much of a role in forwarding the triggering models? Or do you think perhaps that we need to even rethink how we develop the triggering models in light of what we've learned from AI?
Yeah, those are good and really challenging questions, Ben. And yeah, thanks for your kind words. Well, you know, everything in science serves the population well until it's replaced by something else. And it is inevitable that our tools are going to be replaced and made better. And it's probably unreasonable to think that the conceptual approach to a problem is going to persist forever, that the most ideal approach will persist, that is. I think there's some really interesting work lately using tier 3 modeling. So, you know, Mishko, Kubernovsky, Hudebarat and Bray, Basal and Bollinger, using tier 3 modeling to try to come up with what I would say are better predictor variables. So let's look at the mechanics more closely to try to come up with predictor variables that then conceivably could be used in empirical or AI models. That's, you know, they're not taking that to the last step, but I'm trying to kind of point out that I have some vision of how people can respect mechanics and use mechanics to get some better sense of what's going on, but probably there's always going to be an empirical piece. And for that empirical piece, I just don't know of a good reason not to use AI, or a good reason to just dismiss it outright.
Yeah, thanks so much. I'll look forward to chatting with you more casually further.
Brett, you made reference early on to a written description of this presentation on your website. Is that something that's available to people? It's been requested in the chat section.
Yeah, so I think I was actually referring to this this brief editorial that we wrote on the use of Chat GPT.
Oh, okay.
That is online if you find my website in the depths of the internet. But actually also on my website, we've written a paper about this content, and I can post a preprint of that paper. So you can view this in text form.
Okay. Yeah, that'd be great. And I do appreciate your suggestion of using Chat GPT. I think we can finish up the book pretty quickly that way. Does it do figures? Because I've spent like the last 4 days working on figures.
It is terrible at
the
figure interpretation.
Okay. I think we've hit the questions, at least that I have seen. If somebody wants to jump in and unmute themselves and ask another one, we have time. Otherwise, we can probably conclude pretty quickly.
Yeah, I have a question if it's not too late. Kind of on the whole publication angle. You know, as a former journal editor, if I encountered the situation that you described, say using Darcy's law, where you describe some observations, but you don't actually show the model, and there's nothing actually usable out of that. And you reasonably could provide a model. If I had noticed all of that as an editor, I probably would have declined the paper without review. But I did do that a number of times with AI-based models, because I didn't see anything that would be useful to the readership. So I wonder, in your review of many papers on this specific topic of liquefaction that obviously did make it through the review process in good journals, what do you think explains that? How is it that these are making it through the review process without the rigorous testing that you described and without a usable product in the end?
Yeah, thanks, John, for that great question. I'm hesitant to paint anything with a broad brush. I wouldn't want to send the message that you absolutely have to provide a model. I do think in very exploratory research, it could be okay. But I suspect that it's not that people have a different philosophical idea of publishing. If there's one reason, I think it's probably just unfamiliarity with how the models work. A lot of the papers look and sound very impressive, and I think it's probably easy to miss the fact that there actually is no model provided as part of the paper. So I think it's lack of familiarity, if I had to name one thing.
Yeah, you think maybe the fancy words contribute to that as well?
I definitely think there's part of that, yeah.
Yeah, okay, great, thank you.
Okay, well, with that, I think we'll close up this very successful, very interesting, informative, and provocative webinar. Brett, thank you again for preparing this and helping us all understand AI a little better, or at least understand what we don't understand about AI and AI-based methods a little better. So thanks to everyone for participating, and we'll look for another webinar. I don't know that there's one scheduled, but we'll publicize the next one as soon as we have it scheduled. Okay, thanks everybody.